In the previous few lessons, we've been learning about motion in the x dimension with acceleration, or primarily horizontal motion. In this video, we're going to take a different approach, and we're going to be learning about motion in the vertical dimension. And specifically, we're going to be learning about a type of situation that exists in the vertical dimension where an object is in free fall. And those are the situations that we're able to easily analyze in the y dimension because they involve some quantities that we can just infer. We don't have to be told them in our problem. There are some things that we know about the y dimension just because it's a y dimension problem. Let's get started talking about the y dimension and free fall. In the y dimension, it's important for you to note that there is constant downward acceleration in some cases. You see, in the real world, we live on Earth where there is an atmosphere, which is actually a very, very good thing, but makes physics very difficult because the atmosphere interacts with moving objects as they run past the air particles. The air particles collide and resist the motion of anything that's moving. Free fall is a model that we use where things move downward with constant acceleration and are only affected by the pull of gravity. However, in the real world, we only rarely get to observe true free fall because of air resistance. Air resistance is something else that affects downward acceleration other than gravity. So if there's significant air resistance, we can't apply the concept of free fall, something falling toward the earth in the y dimension only impacted by gravity. What is air resistance? Well, air resistance is air particles resisting the motion of objects moving through them. Now, technically, air resistance was always happening in the x dimension as well. It's just in the x dimension, objects don't easily attain very high speed. In the y dimension, on the other hand, because of the acceleration due to gravity, gravity is actually a pretty fast acceleration, so things attain a high enough speed to be affected by air resistance fairly quickly. But the other thing about the x dimension is that when we were working problems in the x dimension, the acceleration was just sort of baked into the problem without having to account for air resistance. So a problem that you were working would say something like a car is accelerating at a rate of 2.8 meters per second squared. It doesn't have to say anything about air resistance because the car is already overcoming that air resistance to travel at 2.8 meters per second squared. So it wasn't really a factor because we were already taking it into account without having to think about it. In the y dimension, because things do attain very fast speeds fairly quickly, and because we assume a lot about the motion of objects moving in the y dimension, we're going to have to pay attention to the effect of air resistance in the y dimension, even though we didn't really talk about it in the x dimension. We're going to find out in this lesson that there are a lot of considerations in the y dimension that are sort of unique for the y dimension. Air resistance kind of is one of them because it also applies to the x dimension. It's just now we're going to have to be thinking about it, especially when we consider whether an object is in free fall or whether air resistance is having a big impact. Because again, if air resistance is having an impact, the object isn't just accelerating because of gravity. Now we have something else affecting it, and it's not truly in free fall. Now, let's just think about air resistance. What does air resistance depend on? Well, first of all, it depends on the speed of the object. If an object is moving slowly, air resistance is probably going to be negligible, depending on other factors as well. Okay, so speed isn't the only factor, but an object moving slowly is less likely to have a significant amount of air resistance pushing back on it. The cross-sectional area of an object matters as well. The narrower, the less area an object covers in space as it's passing air particles, the fewer air particles it's going to catch as it moves, and the less air resistance it's going to have. If an object is moving with a large cross-sectional area, it's going to catch a lot of air particles. There's going to be more air resistance. Okay, so think about dropping a sheet of paper without crumpling it up first. A sheet of paper has a lot of area that's able to bump into air particles, and that's why it's very easily affected by air resistance as it falls. If you crumple it into a small ball, you're minimizing its cross-sectional area as it falls. It's going to fall more easily through the air and be less affected by air resistance and more likely to fall as a free-falling object. Another factor is the shape of an object. You know there are more aerodynamic shapes and less aerodynamic shapes. If an object has a lot of flat area exposed to the air as it moves, it's not very aerodynamic. Think of a big semi-truck trailer rolling down the freeway. If there's a flat area of that trailer exposed to the wind, it's going to catch a lot of air particles. However, if you put something to smooth the front of the trailer so that the air sort of blows up a ramp or a curve around it, it's going to be more aerodynamic. So the shape of an object affects air resistance, and then also the density of the air. And even on Earth, the same air in different places can have different densities depending on the air pressure, just due to shifting weather patterns. Due to the temperature, due to elevation, different things will affect the density of the air as well. All right, so those are some things that determine how much air resistance is acting on an object. It's also important to note that objects accelerating in air, as they go faster and faster, air resistance is going to increase more and more. The speed of an object is the number one factor determining how much air resistance there is. And if you drop something in the air, it continues to pick up speed due to gravity, and it picks up speed fairly quickly. Eventually, there's going to be so much air passing by it that it's going to cause the object to stop accelerating due to gravity and to travel at a constant speed through the air. The object's still going to be falling, so it's still going to be moving at a certain velocity. It's just not going to be accelerating anymore. And we call that velocity the terminal velocity. So here's what that looks like graphically. Here's an object falling in free fall, okay? Its y position is changing over time. And not only is the position changing, it's changing at a rate that's accelerating toward the ground. The velocity is negative because we define moving downward as negative, and this object is moving downward toward the Earth's surface. Okay, and this is what it would look like as it accelerates toward the ground. It covers more and more distance per unit of time, and that means that the curve is going to become steeper and steeper over time. If air resistance is affecting this object, instead it's going to look like this. It's going to accelerate toward the ground at first, but that acceleration is going to slow and slow because more and more air resistance is building up and also affecting how much the object can accelerate. And then eventually acceleration is going to stop and the object is just going to move toward the ground at a constant rate. We call that constant rate the terminal velocity. Notice that between these two vertical dotted lines, my object's path becomes linear instead of parabolic like it was when it was in free fall. When an object's path becomes linear, when I look at a position time graph, a linear position time graph shows a constant velocity without acceleration. And if I wanted to, I could find the value of the times on the x-axis and the positions on the y-axis, and I could calculate the slope of the line between the two dotted lines and figure out what that terminal velocity is. Okay, so that's what happens when there's air resistance. Now, here's the thing. In the vertical dimension, we don't have an equation that very easily deals with air resistance. If you look at that curve, there's two different kinds of motion happening there. There's accelerating motion at first, and then that accelerating motion is leveling off and become linear motion. But even the accelerating motion isn't really a parabola. It would be a parabola if there was no air resistance, but it's a parabola that's changing its parabolic nature even over time because it's not a constant acceleration, it's a changing acceleration. So what I'm saying is air resistance is very, very difficult to deal with mathematically. In physics, what we're going to do right now is focus on problems where air resistance really isn't a factor. So as objects fall through the Earth's atmosphere, no matter what, they're going to encounter air particles and there's going to be some air resistance. However, free fall for us is going to be an approximation. And we're going to assume that in problems that don't mention air resistance as an important factor, the air resistance must be near zero. So that means that the object is going to essentially be falling freely, and its acceleration toward the ground is going to essentially be entirely because of gravity without any air resistance impacting it. Now that happens especially for massive objects that aren't easily accelerated by the air, so gravity is the only thing that can affect those objects and their motion. Slower moving objects, again, we talked about how as an object speeds up, its tendency to encounter air resistance goes up. So objects near the beginning of their fall. And like I said before, part of the problem with free-falling objects in the y dimension is that they tend to pick up velocity very, very quickly because gravity has a fairly large acceleration. So we're going to be observing a lot of objects near the beginning of their fall toward the Earth's surface. And the longer time frame over which we observe an object's falling toward the Earth, the less realistic our result is going to be, because the more likely it would be to encounter air resistance as it speeds up toward the Earth. And then lastly, the more aerodynamic an object is, the less likely it is to encounter a significant amount of air resistance, and the more likely we are to be able to treat its falling toward the Earth as free fall. Perhaps one of the best ways to observe free fall is to go to a place where the atmosphere doesn't actually have an impact on a falling object, like if we were to travel to the moon.
Well, in my left hand I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
We'll find out a little later this year why it is that all objects that are only pulled downward by gravity, only affected by gravity, fall toward the Earth at the same rate, and in this case toward the moon at the same rate. And why air resistance is the thing that causes objects to fall at different rates. On the moon, because there's very little negligible atmosphere, objects fall toward the surface of the moon at the same rate, and that's why the feather and the hammer fell at the same time. Neat stuff. We'll talk more about that later. All right, but let's continue to consider free fall. And in this case, let's watch this video about jumping stilts. We're actually going to analyze the motion of this guy on jumping stilts through one of his jumps in just a moment. These jumping stilts are just kind of interesting to watch, though, as you go toward the ground. And notice that he makes contact with the ground, leaves the ground for a time. When he leaves the ground, the only thing affecting him is gravity. And then when he lands, anytime he's in contact with the ground, there's other things affecting his motion. In the case of the jumping stilts, the thing affecting his motion when he's touching the ground is the spring of the stilts that then launches him back upward, and then he can continue another one of those cycles where once he leaves the ground, only gravity is impacting him. Air resistance in this case is going to have negligible impact because he's not moving at a fast enough speed to have air resistance cause any kind of measurable effect. So let's analyze the motion of these jumping stilts. Here I've plugged in a portion of this video into video analysis, and I analyzed the video to see what his motion was like. Now you can see there's a lot of aberrations here. This video was tough because this person moves a lot more like a system and a lot less like an individual object. I tried to analyze a part of the stilt because the stilts were probably the part in the video that was moving the least. In a case like this, you want to try to measure the object's center of mass As this guy was moving, it was really hard to determine what his center of mass was, and I doubt the stilt stayed stationary with respect to his center of mass. But it gave us decent results. We got pretty good results, so we're going to go with these results as we analyze his motion. This is what free fall motion looks like when you graph it as the y position. Okay, so I'm graphing vertical position over time. Notice that when you look at the actual data points, the data points start at a certain place and they move upward, but at a decreasing rate. The points vertically are getting closer and closer together. And then the person reaches this apex at the top of the jump and turns around and starts coming back toward the ground again at an increasing rate toward the ground. If I were to graph the y velocity over time, notice that the y velocity started out positive. He was moving upward with a certain speed, but was constantly decreasing. It decreased until it reached 0 in the middle of the graph there. And that means that for a moment in time, he was stationary at the apex of his jump, right at the top, but then started to move downward, and his velocity became negative and continued becoming more and more negative as he sped up toward the ground and was actually moving downward at a faster and faster rate. You'll see that this certainly isn't the only free fall graph shape that exists, but all free fall graphs are going to have common characteristics, and this is a very common free fall graph we're going to be observing. So let's take a little bit of a deeper look into what this graph is showing us exactly. Here I have some idealized free fall graphs. Notice that there's no aberrations in this graph because I've taken the equations from the two graphs on the left that were yielded by video analysis, and I've idealized them to take the aberrations out so we can see what an ideal graph would look like. Here's my acceleration time graph. Acceleration due to gravity should be a constant 9.8 meters per second squared directed downward. So we would say the acceleration is negative 9.8 meters per second squared. Make sure that you know that number. Sometimes you'll see it approximated at negative 10 meters per second squared. Unless otherwise told to do so, though, you should always use the more precise negative 9.8 or negative 9.80 meters per second squared. Just want to note too, sometimes you'll see it reported as negative 9.81. Please keep in mind that 9.8 is an approximation based on all of the values that acceleration due to gravity can take on anywhere on the Earth. The further you are away from the center of the Earth, like if you climb a mountain, you're going to have a little bit less acceleration due to gravity the farther you are away from the center of the Earth. And also keep in mind, the Earth isn't really truly a sphere. The Earth is sort of oblong, and different parts of the Earth are closer to its center than other parts. So acceleration due to gravity is going to vary depending on your location. Some physicists approximate it as negative 9.80, some as negative 9.81. We are going to be using negative 9.80 in these lessons. Here I have it as just negative 9.8 because that's the limitations of the significant figures from my experiment. But if I were working a problem and approximating the pull of gravity, acceleration due to gravity, it would be negative 9.80 that I would use. Okay, let's look at what a position time graph would look like if I idealized it. Notice that this is a perfect parabola, and I have the points labeled on my parabola. You can see those there. Notice that my object, in this case the person on stilts jumping into the air, he's above the ground because he's on stilts. And also, I started measuring when he was just a little bit up in the air so I could be sure that at the start of my measurements, he was obviously off the ground. The only thing impacting him was gravity. He wasn't pushing himself off the ground at the moment I started my analysis. So here we have points that go up. They increase in position, but at a decreasing rate because he starts with an upward velocity, but acceleration due to gravity is pulling him downward. So he's going to slow his velocity upward until it reaches 0, the velocity reaches 0 at his highest point, and then he's going to start falling back toward the Earth. What goes up must come down in this case because of gravity. So he's going to fall back down toward the Earth, pretty much back to his original position, which is close to 0.88. In this case, it was 0.86 meters at 0.6 seconds. So the entire trip up and down took less than a second. But as you think back to that video, that's about right. He didn't take a long time to go up and then back down again. And that's just because the pull of gravity on Earth is a fairly strong pull, which accelerates him downward fairly quickly. And then lastly, this would be the velocity time graph. Notice that he started with a positive velocity, but that velocity then decreased more and more. Eventually it became 0 at the halfway point on this graph, right? So he stopped moving upward and wasn't quite moving downward yet. He reached that maximum point where for just a moment he was at rest. And then continued to move downward with increasing velocity toward the ground until his end velocity was negative 2.98 meters per second according to the data. Now there's a key point here that I'm trying to make by lining these two graphs up with one another. Notice that the times are lined up on that position graph and the velocity graph. And I'm just going to put a line on the graph here right in the middle. Notice that where the velocity time graph has the curve crossing the x-axis, so that means that the velocity time curve is 0 at that point. That's a significant point on the position time graph as well. That's the maximum of the parabola, because at that point his velocity is 0, and then it begins to decrease. Notice that that 0 velocity point is at the same time as the maximum of the parabola. That's an important relationship for you to realize. All right, at this point, let's take a look at the actual position time data table and see if we can figure out what the acceleration is according to two different methods. First of all, let's just do a parabolic curve fit. So here I've got the data points. You can see those messy data points that I did my best to collect them. There's some that are above, some below the parabola. But overall, the data basically did fit to the parabola with some aberrations, and I was able to generate this equation for the curve fit for the parabola. From this equation, you can figure out what the acceleration and initial velocity are. Here's my general equation from the kinematics equations for position time with constant acceleration. And I'm just noting that 1/2 a, which is attached to the t squared value, corresponds to negative 4.91, which is on the x squared value in the equation for this parabola. I can figure out acceleration from that by just equating those two. 1/2 a equals negative 4.91, or my acceleration is 2 times negative 4.91. I get that negative 9.8 value, and this data actually gave me really good agreement with what the acceleration due to gravity should have been. Now you'll notice that my data was messy, but because I had several data points, I had some above, some below, when I found the middle of the road result, I got a pretty good measure of what acceleration was. It worked out fairly well. And then just inspecting the rest of this equation, I see that I have in my kinematics equation VYO, the original y velocity, times time. And then in my curve fit equation, I have 2.90 times x. Because x is time, that 2.90 must be that VYO value. So my original y velocity was 2.90 meters per second. And that's a very realistic velocity. For somebody jumping from the ground, it's not going to be an extremely fast speed, but it's going to be fast enough to propel them into the air, and 2.90 meters per second would do that. And then finally, I'm just going to note that that 0.00 is rounded to 2 decimal places. If I were to string that number out further, I would find that there were some values attached to it. but it's essentially 0. It rounds down to 0. It's a negligibly small number. And what that means is that my original position value was 0, and that was simply because of where I put my coordinate plane when I set up the problem. I set it on the first point so that that y0 value would be 0 when I worked out the problem. All right, now here's a question. Can I figure out what the acceleration was a different way? Could I figure it out by linearizing this equation, my kinematics equation, with the data that I have? Let's see how I would do it that way. So I'm just going to keep that kinematics equation, and we're going to continue to look at the position time graph. I want to keep that in front of us. And now let's see if we can just take this data and linearize it. Well, the first thing I should note as we do this is that in order for us to be able to linearize this data, it has to fit into the format of a linear function. And to do that, we're going to examine the slope-intercept form of a linear equation. The only way that I'm going to get this to fit into slope-intercept form is if I don't have an initial velocity. That term has to go to 0. If that was true, then my equation would look like this. Y equals 1/2 at squared. That second term went to 0, so then it's just plus the original position y0. If I have this equation, notice how it corresponds to my slope-intercept form. Y is y. That's nice that now that we're using y for position and it's on the y-axis, those two variables are the same. The next value I need to account for in the slope-intercept form is m. M is not a variable. It has to be a constant value. And so I need to correspond it either to a constant or to a set of constants that are being multiplied together. In this case, I see that m is going to be 1/2 a. Wait a second, is a constant? Well, think about it. We said that in free fall, acceleration is this constant negative 9.8 meters per second squared. And then 1/2 is constant, so 1/2 times 9.8 is a constant value. I'm just going to note it down below because it'll be important to remember this later, but the slope in this case is 1/2 a. So if I do a linear fit and I get a slope value from my linear fit, I need to remember that that slope value is 1/2 of the acceleration. And to figure out the acceleration, I'm going to need to do just a little bit of algebra to find out what that value is. And then what is my independent variable? X, remember, represents the independent variable, what gets graphed on the x-axis of the graph. Well, my x is going to be t squared. So instead of just graphing against time, I'm going to graph against time squared. And then lastly, I don't have an original height, but if I did have an original y position, I would be able to use it because the original y position corresponds to b in my y equals mx plus b slope-intercept form. All right, now let's go back and add in a column to my table of time squared. And I'm simply just going to take all of the time values and square them, and then we can graph our y position versus time squared. And we'll see if this actually does work to linearize our data. You might already be able to predict what the outcome of this is going to be. Are we going to have a linear data set when I graph t squared on the x-axis as my independent variable and y position on the y-axis? And I see that this didn't work. And maybe you caught as we went along why this wasn't going to work. Now, I have the benefit of knowing what the curve fit equation is going into this. Let's just compare our curve fit equation to the general kinematics equation I was expecting to linearize. And notice I said that our linearizable equation had to have a 0 for the original velocity. But our original velocity was significant. The initial upward jump of our power stilt user had a velocity of 2.9 meters per second. So we can't just linearize this equation. It's not going to fit into the y equals mx plus b form. I can correspond the y's, the m's, I can correspond the x value to t squared only, it will not handle another independent variable, and t in this case would have a different value than t squared, but it's still variable. It's still going to be changing over time. And I can even correspond the b in the slope-intercept form, but that 2.9t can't be a part of the equation. So I'm going to go ahead and record the rule that in order for our graph to be linearizable with position, time, and acceleration, we need an initial velocity of 0. And let's consider how we might be able to do that with the data that we have. Maybe we don't have to throw away this entire attempt. Well, is there a time at which our velocity is 0? Remember what happens with free fall. We have an object that's being launched into the air in this case, and it's going to be constantly accelerating at negative 9.8 meters per second squared, slowing down, slowing down, slowing down until it reaches its maximum point, at which time it's going to have a velocity of 0. So what if we only analyzed the velocity of the object and its acceleration, its position, starting at that maximum point? What would I have to do in this case? Well, I'd actually have to get rid of the entire first half of my data because I have data from when the power stilter left the ground all the way up through the air and then returned to the ground. And halfway between leaving the ground and returning to the ground, the person reached a maximum height. Okay, so I got rid of the first half of my data. Here's what that's going to look like on the velocity time graph. Notice that now my initial velocity is 0. And on the position time graph, I just got rid of the entire first half of my position data. Is this going to work? Well, let's try linearizing this, and ooh, still not a linear fit. So as we look at this, we eliminated at least the upward trending data at the beginning, but this definitely doesn't look linear. It still looks like half parabolic. So what's happening here? Well, if we look at the equations that describe our kinematics again, we did successfully get rid of our original velocity term, which helped us get an equation that looks linearizable, right? So this looks like it fits into our mx plus b format really well. Except there's a problem that's actually hiding in this, something I talked about in a previous lesson. You know, t isn't actually just t in this equation, it's delta t. We replaced delta t with just the variable t because it's convenient for us to just keep writing out t squared, instead of having to write that delta t squared, or even worse, t minus to every single time. But here, that's become a problem. T is actually delta t, or t minus to. And because we don't have our t values set to 0, if you look at the graph, our original time is like 0.3 seconds and not 0, that became a problem for us. So if I were to rewrite our kinematics equation, but replace the t with t minus to, because we have a to value now, I have to account for that. And to is a constant. So maybe it won't be a problem, right? Maybe it's just going to be another constant that's a part of this, and it will fit into the constants in mx plus b. Maybe it'll be part of the slope or part of the y-intercept, and it won't cause any problems for us. Well, what does this mean when I'm taking t minus to squared? That's the same as t minus to times itself, t minus to. Okay, and when I FOIL that out, and I'm just going to keep that 1/2 a out in front there, when I FOIL out t minus to times t minus to, I get t squared minus 2t to plus to squared. Well, to squared is just a constant value because my original time, in this case, the original time of this whole thing is 0.3 seconds. If I square 0.3, I get a constant value. And then plus yo. And then I can distribute that 1/2 a to everything. Notice when I distributed it to the middle term, it was 1/2 times 2, so that just became ATTO. Let's try to fit this into slope-intercept form. So my dependent variable is y. That's the same on both sides. The slope is still 1/2 a, My independent variable is still going to be t squared. And then what can I include in b? Well, anything that's a constant can be included in b. YO is a constant, my original position in the y dimension. And then 1/2 a TO squared is a constant. 1/2 is a constant. The acceleration is constant, so that's just going to be negative 9.8. And then my original time is constant as well. I can include all of that in B, but what I can't include in B is anything that has a variable. And t, regular old t that's not being squared, is just a variable that's not accounted for anywhere. So here again, I have this extra value that is making this unlinearizable. So there's one other characteristic I'm going to add to my list of conditions here. TO must also be 0 for this to work, because if TO was 0, then t minus TO squared would just be t squared, because it would be t minus 0 squared. And that's what I need to happen in order for this to work. All right, so can I change my data once again? Can I adjust this so that the original time is 0? Well, the original time is sort of arbitrary. So let's just make 0.3 seconds my 0 seconds point. I'm just going to change the reference moment, right? And then 0.37 is going to just be 0.07. 0.4 will just be 0.1, and I'll change all the other data accordingly. That also changes the t squared values. I need to find the t squared values for those new t values. Okay, now I have different t values that correspond to my y values, so let's adjust my graph. Notice that now my graph starts on the y-axis, and this should be a much more linearizable result. Here I have my general kinematics equation that I can linearize, and the slope-intercept form. And once again, remember, all of these values have corresponding values in the slope-intercept form. So I should be able to take this data and linearize it and then find the acceleration. And lo and behold, this looks much more linear than it did before. And yes, there's some aberrations, but those are fine. At least it's not obviously a parabola, right? So now I'm able to do a linear curve fit to this graph with this equation. And here I have the slope of that linear curve fit, negative 5.276. And remember, the slope is 1/2 the acceleration. I could just work out the algebra here. So I'm just going to multiply that slope by 2 to calculate the acceleration at negative 10.6 meters per second squared. Now, which gave us the better result? The parabolic curve fit to the original graph or the linear curve fit to this graph? Well, if negative 9.8 is acceleration due to gravity, I got a much better result from the parabolic or quadratic curve fit. And part of the reason for that is just because I had more data points. Because I had more data points there, all these aberrations were sort of canceled out by other aberrations in the other direction when I had more data. And that's really the biggest factor that caused this to be different. The other difference is because I always have to pick a starting point on my graph that is an actual measured data point, but is the top of the parabola, the exact top where there is absolutely no initial velocity. Think about it. The very, very top of the parabola is where the original velocity is 0, right? So I have to pick that point to have the perfect 0 velocity and then do a linear curve fit where VO equals 0. Is one of my data points going to be that exact perfect point? Probably not. I'm probably going to have a point that's at least a little bit off from the maximum of the parabola. And that adds a little bit of error to my data as well. Negative 10.6 is a good calculated value for gravity. It's close to negative 9.8. The percent error is not that great, but it's not the best. The parabolic curve fit worked much better. All right, moving onward. Let's think about typical characteristics of y-dimension problems and how they're different from x-dimension problems. The graphs look the same. All right, we're going to be generating velocity time, distance time, and acceleration time graphs that look similar, but there's going to be some things that are unique. First of all, in a horizontal problem, you either had to measure or be given the acceleration that was occurring in that horizontal problem because it was being applied by an engine, or it was occurring because brakes were being applied. And those don't have like constant values of acceleration that everybody knows. But the acceleration caused by gravity is a constant on Earth that we know what it is. The value for the magnitude of acceleration due to gravity is 9.8, and we represent that with the variable g, okay? Now notice that I've been saying negative 9.8, and this is a positive 9.8. The magnitude of acceleration is just the value that the constant g has, and then we just observe that because acceleration points downward on the Earth's surface, as long as your frame of reference has downward being negative, most of the time in these problems, the acceleration in the y dimension is going to be negative the constant g, or negative 9.8 meters per second squared. I did a little bit of extra mathematical notation here to show you that g is always reported as a positive value, but the acceleration due to gravity is usually just negative 9.80, so negative g. And that value you just know for vertical problems. They don't have to tell you as you're working problems or as you're designing an experiment in the vertical dimension. You don't have to always measure acceleration due to gravity. You could just assume it's negative 9.80. And if you need to be really precise, maybe you need to measure it for the exact spot where you are on Earth. But for the most part, negative 9.80 is a valid and precise approximation that you can use. What else do we know? Well, when we have a constant acceleration of negative 9.80, our graphs are always going to have a very similar shape. They're going to be concave down parabolas. Here's a possible parabola. Note that this would be like if we were throwing a ball off a cliff. It's going to go up for a little bit. We launch it upward into the air. Gravity is going to take it and pull it down past our original vertical position, and it's going to continue to go downward until it reaches whatever's at the base of the cliff. Or throwing a ball out the window, it's going to go up for a bit and then continue going downward until it reaches the ground. Our velocity time graph would show that at the maximum of the parabola, we're going to have zero velocity. That's where the velocity time curve crosses the x-axis. It's going to start with a positive velocity, and that velocity is going to become negative. Let's take a look at another sample graph. This is like the one that we just analyzed, where an object starts at the same place that it ends. In the previous one, though, it started above the ground because we were considering the point where the person on power stilts was already up in the air. This would be something that launches from the reference point at 0 and then lands back at the reference point after some time. Once again, here we're going to have an initial velocity. That curve is going to cross over the x-axis and be 0 at the same point as the maximum of the parabola, and then it's just going to continue and become more and more negative with a constant acceleration. And then lastly, maybe we're only analyzing half of a parabola. This would be an object that's dropped, not thrown up into the air first, okay? So in the previous, we have an object that's moving upward into the air initially, reaches a maximum, and then falls back down. This is an object that's dropped from rest. Notice that my x-axis crossing point is right at the beginning, where my velocity starts at rest and then becomes increasingly negative as acceleration causes the velocity to, in this case, I guess, decrease, become more and more negative over time. Okay, so these are some typical freefall graphs that we might see. Do these look similar to graphs that we would have seen in the x dimension? I just want you to think about that for a moment as we continue onward. We'll take a look at some corresponding x dimension graphs in just a bit. Here's another important point about freefall. the position time graph is symmetrical across the axis of the parabola. So let's just consider this person is head dribbling a soccer ball, and we're going to consider the motion of the soccer ball during one of these bounces. Notice that it's going up into the air, it's launching from his head, and going up into the air and then landing back on his head. So it's ending at pretty much the same position as it started. Okay, so here was my video analysis tracking of the ball, and here's the data that I collected. I just set the reference point at the person's head, where the ball actually launched from, and notice that it went up in the air and then came back down again. It's really small in this slide, but you can see that the acceleration value in this parabola is negative 4.893. Remember that that's 1/2 a. Just like before, let's consider an idealized version of the data. So I just generated these points based on the trend equation for the parabola that we found before. And if I consider this parabola, I notice that between the top 2 points, my actual collected data points, I have this maximum point of this parabola. That's the point at which the vertical velocity of the soccer ball is 0. It's at rest for just a moment, and it begins to fall back downward again. Can you think of where that point is going to be on a velocity time graph? Well, if I look at this velocity time graph, there's going to be that same point, except it's going to be right in the middle. So if at the beginning the soccer ball left the person's head at 1.8 meters per second upward, an initial velocity upward of 1.8 meters per second, and then went up into the air and fell back down again, what do you suppose the speed is going to be at which the soccer ball lands on the person's head after it has gone through the entire up-down motion, and if it's falling back to the same height from which it left? Well, it's important to realize that if we have an object that's leaving from the reference point, traveling vertically upward, being accelerated by gravity the entire time, and then falling back down again to its initial position, it's going to have the same speed except negative. And that's part of the symmetry of the parabola. Because it's symmetrical across its axis, its speed at the same position on the other side of the axis is going to be the same, just negative. That's why this ends at negative 1.8 meters per second. And if that time is at 0.37 seconds, can you figure out what the time that it was moving at 0 meters per second was? Well, it's going to be halfway between 0 and 0.37. Now, I wish I could include this point as 3 decimal places, but I actually have to round it off to 2 decimal places for significant figures. So I would have written it as 0.185 seconds, but I actually have to put 0.19 seconds. It's halfway in between, though, because everything is symmetrical in a parabola. So if an object is launched into the air from a reference point and then falls back to the same reference point a certain time later, it's going to have reached its maximum halfway in between the launch time and the land time. And also, it's going to land with the opposite speed as it started with going upward into the air. Those are some important symmetry points to grasp that only work in the y dimension, where we have gravity that's constantly pulling things downward with a constant acceleration. So why didn't we notice this in the x dimension? I mean, we were working with the same sorts of parabolas in the x dimension, and parabolas are just always symmetrical across their axis. So it's not like we shouldn't have seen this before, right? Well, in the x dimension, we didn't have the other half of the parabola ever. An object was at rest, and then it started accelerating and picking up speed, like the jet that took off from the runway in the first graph. The jet started accelerating, picking up speed, but it wasn't like the jet started off going backwards and then was going backwards more and more slowly until it came to rest and then started launching forward. We didn't have the other half of the parabola. The same is true for the second graph of the braking car that's slowing down. Once the car reaches its maximum position, the maximum of the parabola, it stops. It's not like it continues to accelerate backwards and then goes back the way that it came at an increasing speed, an increasing negative speed, right? We didn't have the other half of the parabola. But when you throw something into the air, gravity continues to act downward on it. So you will have both halves of the parabola, the upward half and then the downward half. Except in cases where you just drop an object from rest or throw an object downward, then you're not going to have the upward half of the parabola. But you can make sense of graphs like that too. The point is that in the y dimension, you're more likely to have both halves of the parabola, and that's why we need to pay attention sometimes to how parabolas are symmetrical. All right, let's consider one more real-world example. In this case, we're going to look at a diver diving into the water, and here I tracked the motion in video analysis so that we could analyze the jump up and then downward into the water. Now, is this a symmetrical parabola? Well, yes, it is symmetrical across its axis. The problem is that when you have a parabola of an object that doesn't land at the reference point, this diver lands below where we started, below the initial reference point. The symmetry of the parabola isn't as useful in this case. Now, we could still maybe use the fact that the diver did reach a highest point at which her velocity was 0 for a moment to figure out some of the physics. We can still use some of the characteristics of the parabola to solve for some things, but we can't just say that the diver's speed when hitting the water must be the opposite of her speed leaving the diving board, because she was falling for a much further distance and longer time between her highest point and the water compared to when she left the diving board and the highest point. So you do have to be able to reason your way through a parabola like that and recognize when the symmetry of the parabola is going to be helpful. So here we can see that the velocity is more distributed to the right of the maximum. We have more of a decrease in velocity on the right of the maximum of the parabola than we do on the left. And therefore, that we're going to have a greater decrease in velocity after the maximum of the jump compared to before the maximum. And those are the sorts of things you need to be able to think about as you're working problems with free fall. So now you know a little bit more about free fall, the y dimension, and how it's different from x dimension problems. Especially, you know that there are some assumptions you can make about problems you're working in the y dimension. You can make the assumption that the value of acceleration due to gravity is negative 9.80 meters per second squared. Sometimes you'll use negative 10 as an approximation. You can also assume that the parabolic motion will be symmetrical across the axis of the parabola if you have both up and down motion. And you know that that's going to be the most useful when you have an object that's being launched from a reference point and then lands at the same height as it was launched.